Hello everyone. Today we are going to study about routing algorithms, right? The topic of discussion is routing algorithms with respect to network layer. In the previous classes we have discussed about forwarding, right? We have discussed about forwarding, how forwarding of packets takes place in the network layer. Now we are moving on to the next basic functionality of the network, or basic service, the important service that is being provided by network layer is routing. So we are going to study about routing algorithms in today's class. Before moving on to routing algorithm, first let us learn few basic concepts. So the very first basic terminology is default router. So what do we mean by default router? Each host, when I say host, it can be a computer or anything which is connected to a network. Each host is connected to its nearest router, right? So each host is connected to a nearest router, and that router is called as default router. Okay? The default router that is connected to the source. Since we are talking about routing, it will be between source and destination, right? So the default router that is connected at the source host is called as source router, and the default router that is connected at the destination host is called as destination router. So any host is connected to its nearest router, that is called as default router. The default router at the source end, at the source host, is called as source router, and the default router that is at the destination host is called as destination router. Since we are talking about routing, it will be between two different hosts, right? For example, as we have all discussed in the previous classes, there will be a network, there will be some host somewhere over here in this network, and I will be having some other network here, and I have my destination here. So this is my destination and this is my source host, right? Source host will be connected to one router and destination host will be connected to some other router. So this becomes my source router and this is my destination router. In between, I will be having several routers through which we can traverse, right, from source to destination. So in the routing algorithm, we are going to discuss about this portion, that is between source router to destination router, how the packets, through which path the packets are traversing. Okay, that is what we are going to discuss under routing algorithm concept. So learning about default router, source host and destination host, we will move on to the next thing, that is graph. Okay. The next is graph. We use graph in order to implement this routing algorithm. Graph is usually represented something like this, right, where we represent number of vertices and E represent number of edges that exists between these vertices, right? This is how we represent graph. We use the same concept of graph in routing algorithm also, where we represent the number of nodes or routers here. Nodes or routers here, and E represent the number of physical links that exist between these routers. For example, consider this diagram. Okay, 1, 2, 3, 4, 5, 6. If I consider this as a network topology, here all these 1, 2, 3, 4, 5, 6, all these nodes represents the routers in the network, whereas these links, okay, these links represents the physical links or the physical connection between each router. Okay, so these constitutes our V in the graph, and these edges constitutes our E in this graph. Each of these edges here in this graph will have a weight some 2, 1, 4, 5, 3, 2, some weight which is calculated based on some criteria. Okay, each of these edges or links between these routers will have a weight which is used in order to calculate the path or optimum path between source and destination. Okay, so depending on these cost, we are going to calculate the least cost that can be used in order to travel from source to destination, and we call that as least cost path or shortest path. Okay, what do we mean by least cost path? It is a path which contains the nodes or the route through which our packet need to traverse from source to destination with the minimum cost. How the minimum cost is going to be calculated? It is going to be calculated with the help of these weights. These weights are calculated based on some criteria which is of not concern for us at this time. Okay, so this is about the least cost path or shortest path and the graphical representation of our network. Okay, now after this we will move on to the classification of network. Having understood about the graphical representation of network, routers and the physical links between them, now we will move on to the next topic, that is how can we classify the routing algorithm. We got plenty of routing algorithm. Based on few criterias, we are going to classify that routing algorithms under the network layer. Okay, so the next topic is classification. Okay, classification of routing algorithm. The classification of routing algorithm can be done in 3 ways. Okay, the very first option or the very first criteria is whether it is global or decentralized. Okay, the second criteria is whether it is static or dynamic. Third one is whether it is load driven, load sensitive or load insensitive. Okay, these are the 3 criterias based on which we are going to classify our routing algorithms. The very first criteria is whether the algorithm is going to make use of global understanding of the network and about the calculations. Okay, and the second criteria is static or dynamic, and the third one is load sensitive or load insensitive. Now we will learn each one of this separately. According to the first criteria, we have global routing algorithm. What do we mean by global routing algorithm? In this particular category of algorithm, one need to have the complete knowledge about the network topology. Okay, you need to have a knowledge about the complete network topology, and you need to have a knowledge about all the weights of each link in the given graph, right? You need to have complete information about that in order to find the route between a source to destination router. Okay, so here this is the criteria based on which we are going to calculate the least cost path. The very well known algorithm which falls under this category is LinkState algorithm, which we are going to study after this. LinkState algorithm. Okay. Under this category we find LinkState algorithm, which we are going to study further next. Okay. So, this demands us to have a complete knowledge about the network topology, what are all the possible routers are there, what are all possible edges, links that exist between all these routers, and how these links are connected to each other, and what are the weights that are associated for each of these links. Depending on these inputs, we are going to calculate the distance, least cost path from the source to destination in case of global routing algorithm. The next is decentralized. Decentralized algorithm. Under the first criteria, the one is global routing algorithm, and then we have decentralized algorithm. What do we mean by decentralized algorithm? Here we need not have complete information about the network topology at a beginning itself. As and when it moves on to the next iteration, the values, the data is going to be updated. So, it works in an iterative mode. Okay. Works through iterative mode, and it is not centralized. In case of global routing algorithm, the information is centralized, everything is should be available at the beginning itself. Here it is not like that, it works on iterative and distributive manner. Okay. So, the very well known algorithm which falls under this category is distance vector algorithm. Okay. Under distance vector algorithm, for each node we will calculate the distance vector for all the corresponding immediately connecting neighbors, and we are going to update it as and when we get new values from the neighboring nodes. Okay. We are going to study about this algorithm also going further. So, this is under the first category of classification. Under second category of classification, we have static routing algorithm and non-static. So, what do we mean by this? Static routing algorithm is the one which changes route, which changes the route between source to destination very rarely over a period of time. Okay? It changes the route over a period of time. Okay? Depending on the network changes. In case of non-static, or we also call this as dynamic. Okay? In case of dynamic routing, the route changes, the route between the source and destination changes dynamically with changes in the network. As the network topology changes, as the network changes, network condition changes, the route changes dynamically, instantly in case of dynamic routing algorithm, whereas in case of static routing algorithm, the route between the source host or source router to the destination router changes over a period of time. So, it is considered as static there. Okay. This is about the second criteria of classification. Next, moving on to the third criteria. That is load sensitive and load insensitive. So, what do we mean by this? In a network, if there is any congestion occurs, okay, if there is any congestion occurs in the network, then the value or the weight that we are going to have for each link in our graph, in our network, is going to be changed depending upon the congestion or load that is happening in the network. That is in case of load sensitive. The reverse of this is load insensitive, in which the weight between any two routers is not going to be changed depending on the congestion that is happening in the network. So, these are the three criteria based on which we are going to classify the routing algorithm, right. So, to conclude, in the first criteria, it is global algorithm, centralized algorithm or decentralized algorithm, and the second category of classification is load sensitive and load insensitive, and one more category of classification is static or dynamic routing algorithm. So, having a knowledge of these routing algorithm, we will move on to understand link state routing algorithm in detail now. Okay. Having a knowledge about different category or classification of routing algorithms, now we will move on to our next topic, that is link state routing algorithm. As I already told you, link state routing algorithm makes use of global routing algorithm concept. It is centralized. That means at the initial state itself, need to have a complete knowledge about the network topology and all the weights that are associated with each of these edges or links in the network. Okay. So, this link state routing algorithm is used to find the shortest path. Okay. We are going to make use of this algorithm to find the shortest path or least cost path from a source to all other vertices in the graph. Okay. So, with the help of link state routing algorithm, we can find the shortest path or least cost path from a source router to all other routers which are there in the network. Okay. This is the algorithm which we have. Okay. So, before moving on to the algorithm, let us consider these three terminologies that we are using in this algorithm. We are using D of V to represent the cost of least cost path from a source to destination. For example, if I consider U as my source, so what is the cost that it takes when we travel from U to V? Okay, that cost of the least cost path is stored under D of V. Okay, and then what do we mean by P of V? We are going to store the previous neighbor of V. When I say a path from U to V, it might traverse through various other routers in between. So, we are going to store the previous neighbor of V which comes in that particular path. Okay, that is P of V. Okay, then comes N dash, which represent the subset of nodes among all the nodes. It is the subset of nodes that are in the least cost path. When we start finding the least cost path from one source to several other nodes, which are all the nodes that are covered in the least cost path at that particular iteration, that is going to be stored under N dash. Okay. These are the terminologies, are the terms that we are making use of in case of this link state routing algorithm. Now, we will have a look at algorithm. This algorithm consists of two steps. The first step is initialization, and then it consists of loop. Okay. There are two steps. From the step 1 to step 6, it is initialization. The rest of the steps from 7 to 12, it is loop. Okay. So, this is about link state routing algorithm. In this, each router will share its information to its neighboring router. At the same way, the neighboring router also shares its details, its information to the source router also. Okay. Using that information or using those information, we are going to calculate the least cost that it takes in order to transfer a datagram from source host to destination host through various routers. Okay. Now, looking into each step. The very first step is initialization. Here we are considering U as the source. Okay. Considering U as a source router. Okay. We are pushing that to our N dash, the set in which we are keeping our nodes which are already traversed. Okay. So, N dash. Okay. Then for all nodes V, if V is a neighbor of U, if we consider U as a source, for all V, which are all nodes that we have as a neighbor to U, which are directly connected to U, for all those nodes, what we are supposed to do? We are supposed to calculate D of V. What do we mean by D of V? D of V contains the cost or weight that it takes in order to travel from U to V. So, for all these nodes which are directly connected to U, which are neighbors of U, we are going to calculate the cost, least cost that it takes in order to travel from U to V, and whatever weight is being attached. For example, from U to V, if we have 1, here if we have 2, and again here if we have 2. So, what it becomes? It becomes D of V will become 1, D of W will become 2, similarly D of X will become 2 for us. Okay. Whatever cost or weight is associated with that particular link, physical link between U and V, will be assigned as the value for the D of V. Okay. That is the first initialization that we are going to have. Otherwise, D of V is infinity. That means, if a new vertex or new router or new node is not the immediate neighbor of U, then assign value for them as infinity. For example, if I have some vertex Z or some S or T which are connected through some other nodes in between, in that case assign value of them, D of Z as infinity, D of S as infinity to begin with. So, this is the initialization portion. Okay. Once it is done, then we will start loop. Okay, what do we do in loop? In loop, find W which is not in n dash, means we have marked U in n dash, right. Initially we have started with the source, okay. In n dash we had our source host or source router, and then as we go on iterations, we will have few more nodes which enters into U. So, that is what we are going to do here. Find W which is not in n dash, it should not be in n dash, and it should be the neighbors of U. If I consider the previous example, that is VWX, which are neighbors of U, and we have values for them, okay. So, consider any one among them. How to consider that? Their value, which value among these three are minimum, consider that particular node. For example, if D of W is 1, these two are 2, then consider W as the next node, and what I should do? Add that to n dash. So, add W to n dash, okay. After adding this, what should I do? Update D of V for each neighbor V of W. Now, I have W, okay. I will be having several neighbors for W, right. So, update D of V, the cast for each of these links which are immediate neighbors of W, okay. How to update that? Using this particular equation, okay, using this particular equation which is proposed by Dijkstra, okay. Using this particular equation, you update the value of D of V. What is that going to do? D of V is minimum of D of V, which we already have, okay. We are already having D of V value for these things. If we find some other path to the same, for example, if I have V as its neighbor and cast of W comma V is 2, I have one more route, sorry, cast of W comma V is 3, and I have one more path from which I can reach V, which casts around 2. That path goes from X, okay. In that case, I need to consider this, okay. So, minimum among these two is this. So, that will become the updated value for D of V. Repeat this process until n dash is equal to n, means we travel all the nodes which are there in the network, we are going to repeat this procedure, okay. This is the theoretical explanation of the algorithm. Now, we will try to understand this in a much better way with an example, okay. Now, we will try to understand our link state routing algorithm with the example. This is the example of network which we are going to consider. Here we are considering U as our source, okay. U becomes our source. What are all the things that we need to store or that we need to calculate at each iteration, okay. The very first thing is we need to initialize. As we have seen in the link state routing protocol, we need to have initialization first, right. What are the things that we are going to initialize? First, when we consider U as our source, we are going to assign U to n dash, the set, right. We are going to have it here in this set, right. And for each of these routers, we are going to calculate D of V, that is cost that it takes in order to traverse from the source to it, to that particular node, and then the P of V, that is the previous node or the previous router that it has to traverse through in order to reach that particular node, right. So, when I am considering u as my source, which are its neighboring nodes which it can traverse directly, v, x and w. So, we have v, w and x which can be traversed directly from u, right. So, what is the cost that it takes? So, d of x becomes 1. So, d of x becomes 1 here, right, and it should pass through x. For v, it takes 2 as weight. So, d of v becomes 2 and it is v. Okay. D of w is, it takes 5, weight 5 to reach w. So, d of w is 5 and it is travelling through w. So, these three are the direct neighbors which are there for our source u. We cannot reach y and z directly. So, those things are kept as infinite at the initial state. Now, in the first iteration, we are entering the loop now. So, we have u here in n dash. What are we supposed to do? We need to find w in such a way that the cost is minimum and it should not be covered in n dash. So, we have 3 casts here, right, 2, 5 and 1. So, which is minimum among them? 1 is minimum. So, we are going to push x to our n dash, the set of vertices. Okay. So, this is finalized. Okay. Now, d of x for this particular node is finalized. We pushed it to this n dash. Now, let us update the value for the remaining nodes. So, what is going to be the value of d of v? For v, we have 2 here. If we pass through x, it is 1 plus 2, which is 3. Now, we need to check using Dijkstra's equation whether 3 is less than 2, no, right. So, we need to consider the minimum of these two. So, we have 2 which is already there. So, same thing is retained. So, same path is considered as least cost path from u to v. If we take this route, it will cost around 3 for us, which is more than this. Now, for w, we have 5 here, right. We have 5 here. If we take this path, okay, from u to x it is 1, from x to w it is 3, 1 plus 3, which becomes 4, right. So, we have 5, 5 is greater than 4. So, we need to consider the new path, that is 4, through which router it has to pass in order to reach w with the cost 4, it is x. So, w is going to be replaced by x, right. Now, y, can we reach y through x? Yes. From u to x we have 1, from x to y we have 1, 1 plus 1 is 2. So, with the cost 2 we can reach y through x, right. Can we reach z from x directly? No, z is not the neighbor of x here. We have v, w and y which is updated at the moment. So, this is kept as infinity at this point. So, moving on to the next iteration, right. The next step, we have u and x in n dash. Now, find out the minimum among the remaining nodes. We have v, we have w and we have y which have cost. Here it is 2, 4, 2. Arbitrarily we will select y here, we push y now. Okay. So, when I am pushing y here, this value is finalized, right. So, we recalculate the remaining values for d of v. So, what is d of v? Can we pass through y in order to reach v? No, it is 2 here. If I take u to x, that is 1, x to y it is 1, 1 plus 1 2 plus 1 3 plus 3 6, that will cost more. So, we retain the same. What about W? Can we reach W, which is the neighbor of Y? Yes, we can reach W with cast 1 from Y. From here to here, it will take 2. 1 plus 1 plus 2, 2 plus 1 is 3. So, with the cast 3, we can move from U to W through Y. So, we are going to update this value. So, this becomes 3Y. Okay. This is finalized, we are not going to touch it, and this is finalized. Now, find out the one more neighbor of Y, that is Z. So, what is the cast that it takes to reach Z? From U to Y it is 2, right? From U to Y it is 2, from here to here it is 2. 2 plus 2 is 4, right? Isn't it? So, this is the thing which happens at second iteration. Moving on to next iteration, what we are having, we have U, X, Y in hand. We have 3 routers now with V with 2, W with 3 and Z with 4. The minimum cast among this is V. So, we push V to N dash. So, our value is finalized here. We are not going to touch it again. Okay. We need to recalculate the values for W and Z. What is the cast for W? We have 3, Y in hand. Is there any other way to reach W through V? Yes. From U to V we have 2, from V to W we have 3. That is 2 plus 3, which is equal to 5, right? But we already have a path with the cast 3 if we pass through Y, that is 1 plus 1 2, 2 plus 1 3. So, we are going to retain the lesser cast path, right, for W. For now, we will calculate it for Z. Is there any other way to reach Z through V? Is there any other path? Just check out. We have 4 now. If we pass through V, 2 plus 3, 5 plus 5, 10, that is more again. 1 plus 1, 2 plus 1, 3 plus 5, 8, that is again more. 1 plus 1 is 2 plus 2 is 4. So, this is the optimum path that we have here, right. So, we retain the same thing here, isn't it? So, at the end of this, we will move on to the 4th iteration. We have U, X, Y, V, which we are left with 2 vertices or 2 nodes, 3Y and 4Y, that is W and Z, which is having minimum cast. We have W with minimum cast 3. So, we push that to N dash. So, 3, Y is finalized. Is there any hope for changes in this particular thing? Is there any other path? Just check. We do not have any other path left with which we can reach Z with lesser cast. No, right. So, we retain the same thing, right. So, at the end of 4th iteration, we have 4, Y. We left with only one vertex now. So, we have U, X, Y, V, W and one more vertex, that is Z, which is left out, is pushed on to N dash. So, this value is also finalized, right. This is how we are going to find the least cast from vertex U to all vertices that are there in the graph. Now, I can write the least cast path from U to all these vertices. How to do it? From U to V. From U to V, I have cast 2 which pass through V itself. From U to X. From U to X, it takes cast 1 and it is direct, right. That is the shortest path. From U to W. From U to W, it is taking cast 3 when it passed through Y. okay, means when it passes through Y, it takes W. W can be reached with a cast 3, okay, from U to U, V, W, X, Y. From U to Y, it takes weight 2 when we pass through X, okay, this route. From U to Z, it takes weight 4 when we pass through Y, that is U to X, X to Y and Y to Z. So, these are the least cost path or the shortest path that we can have for this particular network with so and so weights for each of these routes. So, now we have determined the shortest path from the vertex U, which is considered as source in our example, okay, to all the vertex here. From U to V, it is direct with cast 2. From U to X, it is direct with cast 1. From U to W, we are taking path Y. So, we need to travel to Y and then to W with cast 3. From U to Y, we are taking weight 2 through X. So, U to X is 1, from X to Y it is 1. From U to Z, we are passing through Y with minimum possible cast, that is 4, 1 plus 1 plus 2. So, this is how we can find the shortest path from a single source, from source U to all other possible routers in the given network. So, this is about our link state routing algorithm. We also call this as Dijkstra's algorithm. Okay. So, this is, as we have already discussed, this is a global algorithm which makes use of the link state which makes use of the weight that is being given to all the physical links that are available in the network. In the next class, we are going to study about the distance vector algorithm, in which we are going to discuss about decentralized approach of routing algorithm, in which case we are going to update the routing algorithm at every iteration that we pass through. And one more thing, if you have observed here, we have how many vertices? We have 1, 2, 3, 4, 5, 6. We have 6 vertices or 6 nodes in the graph. And how many paths or iterations that we had? We have 6 iterations. Okay, we have same number of iterations have as that of number of vertices in the given network. Okay, so this is about link state algorithm. Thank you.